Very good.
Ladies and gentlemen,
Started immediately.
we're very pleased to have as our keynote speaker the director of the Green Bank Observatory, Dr. James Jackson. He has adjusted his schedule a couple or three times in order to be able to accommodate us. So it is a real privilege to have him here today, and I hope you'll welcome him. He's been director here at Green Bank since 2021. Previously, he served as associate director for research at the Stratospheric Observatory for Infrared Astronomy, that's SOFIA, with the university's Space Research Association. He's also led administration and research in astronomy and astrophysics for the University of Newcastle in Australia and Boston University. He served as assistant director for the Center of Astrophysical Research in Antarctica. He's widely published. He is recognized for his research into star formation, galactic processes, and the study of deep space molecular emissions. Those of you who have mentioned this to me, I checked it out myself. His Boston University lectures on the fundamentals of radio astronomy provide a foundation for understanding principles of antenna design and signal analysis. And those lectures, which are available online through Boston, are suitable and accessible for amateurs through advanced professionals. And of particular relevance is his explanation of beam patterns, directivity, gain, and effective area, antenna temperature, and sources of side lobes, all of interest to us. So please welcome Dr. Jackson to his own auditorium.
Thank you. I'm impressed at the archaeology that you've done there. That's pretty amazing. That's very nice. Thanks for having me here, folks. It's really great to see you here, and I'm hoping you're enjoying Green Bank as we do every day. It's a beautiful spot. We do some really exciting work here. So in my talk today, I'm going to spend the first half of the talk telling you what it's like to be the director of Green Bank. What keeps me up at night? What keeps me going in the morning? And then I thought I would talk about science for a change, right? Rather than budgets and grout and track, I'll talk about some of the science that I have done with this telescope to give you a flavor of what we can do with this amazing facility. All right. So, how do I advance? There we go. Okay. All right. So here's what we do at the Green Bank Observatory. We use the Green Bank telescope. That's the star of the show, and I'll talk more about that in a minute. And have you had the pleasure of going on the telescope yet? Have you? Wednesday morning. Excellent. Some of you have been on the telescope. It's amazing. Every time I go on, I'm just still impressed with that feat of engineering. So what do we do here with this big single dish? Probably our most interesting work lately is that of gravity waves and neutron star physics. And we do that by timing the signals from pulsars. Pulsars are rotating neutron stars. They're amazingly accurate clocks, and we use them as kind of little test particle clocks to measure the properties of space and time throughout the galaxy. We can catch the passing of a gravity wave by noting some distortions in space-time, and these the timing measurements of pulsars in various directions will denote the passage of a gravity wave. More about that in a moment. The thing that I'm most interested in terms of my own research is the interstellar medium, star formation, galactic structure. This is the gas between the stars. This is the stuff that makes the stars. And by using spectroscopy of atomic and molecular lines, we can figure out what's going on, how that gas is moving, what it's composed of, how hot it is, and what's happening on the way to becoming a star. Another thing that we do quite well here is astrochemistry. About a third of all molecules known in the interstellar medium were discovered right here at Green Bank Observatory. About 8% of them were discovered with the now mothballed 140-foot telescope, and about 24% were discovered with the Green Bank telescope. And we continue to discover new molecules every day. And finally, I'd like to talk to you, this is not well known, but we do radar studies here as well, both as a receiving station. So Goldstone in Southern California, the JPL Goldstone telescope that's part of the Deep Space Network transmits a signal, we receive it, and we can do radar studies that way. I'll show you some of that. And we're also trying to develop our own transmitter. With the tragic loss of the Arecibo telescope, we have lost quite a capability in transmitting radar signals, and we're hoping to pick up some of that slack by developing our own high power radar system. Star of the show is the Green Bank Telescope. It's the world's largest fully steerable telescope, 100 meters diameter. There is one larger telescope. That's the FAST telescope in China. It is not fully steerable. It has to wait for things to pass more or less directly overhead. That is a 300 meter, it can illuminate about 300 meters at any given time. It's 500 meters total diameter, 300 meters are used at a particular time. But our advantage is we can point anywhere in the sky. And that means that we can see about 85% of the sky from Green Bank. We are protected by 2 radio quiet zones. There's a national zone and a West Virginia zone. More about that later. And we cover a very broad range of frequencies from about 400 megahertz up to 116 gigahertz. It has this beautiful off-axis design. So the telescope vertex is actually at the base of the feed arm there. So we're looking at a section of a parabola rather than having our receiver in front of the parabola. It's off to the side. And that makes for very clean optics, makes our spectral baselines beautiful. It also makes our telescope very efficient. It weighs about 17 million pounds. There are 16 wheels, so each wheel is carrying about 1 million pounds. And the contact area is about 10 square inches. So you can do the calculation of the pressure. It's a lot of pressure. It's like stacking 250 elephants on that one small stack. And it's about 480 feet high, taller than the Statue of Liberty, slightly shorter than the Washington Monument. So radio astronomy uses both single dishes and interferometers, and we like the single dish here. We have a big single dish, and they're very complementary in their missions. A single dish can look at very wide field emission from very faint signals. So low surface brightness, large scale emission is what the single dish does very well. It's good for mapping large surveys. It's also nice that there's only one focus. So there's only one place to put a receiver. And so we can develop new receivers fairly easily. If you were to develop a receiver for ALMA, or the very large array, you'd have to develop dozens of them rather than a single one. So we're a good test bed and we're a good training ground for new students and new instruments. The real advantage is that you have all this collecting area and you can replicate that collecting area. So instead of just having a single pixel receiver, we can have receivers with many pixels. We call them radio cameras. We have a camera. Our biggest camera is not megapixels like on your phone, but it is 16 elements. We have another camera with 7 elements. Now that doesn't seem like much, but it's 16 times faster than we could have done before. So we can map that much more quickly. It's really a big improvement in our efficiency. Now on the other side of this coin here, we have the interferometers like the VLA or like ALMA. And they are sensitive to very high surface brightness, so very bright things, and very fine detail. So you use interferometers when you're interested in dissecting the fine details from a single bright target. Now, interferometers tend to use smaller telescopes, so they're easier to maintain mechanically. It's much easier to maintain a 25-meter telescope than a 100-meter telescope. But they're harder electronically because you have so many receivers and you have a giant correlator system as well. So they serve different purposes in the astronomical world. So let's talk about some of the science we've done. And as promised, this is the biggest news I think we can tout. In a couple months ago at the National Science Foundation, the NanoGrav team, which is a group of US and Canadian astronomers, found compelling evidence for a gravity wave background. And these gravity waves are very long wavelength, light years long, and very low frequency, nanohertz, right? 1/10⁹ hertz. These gravity waves are coming from all directions. So now how do they do that? Well, the Green Bank telescope is a major player, provides about 50, they use many telescopes, but the Green Bank telescope is one of the best telescopes that they use. They used to use Arecibo. Arecibo is no longer available. So we're kind of the workhorse telescope in this study. And what they do is they look at the pulses of pulsars and they can predict when they should arrive based on historical data. And sometimes they'll arrive a little early, and sometimes they will arrive a little late. And then what you do is you correlate which on the sky, where all the ones that are arriving early are and where all the ones that are arriving late are. The passage of a gravity wave has a particular angular pattern. Pulsars that are close together in the sky, if this one's early, that one should be early. They should be correlated. But if they're 90 degrees apart, they should be, if this one's arriving early, coming right at you, the 190 degrees apart will be arriving late. They'll be anti-correlated. So there's this unique quadrupolar pattern, and that's to do with the fact that gravity waves are squishing space-time. And there's compressing it in one direction and stretching it in the other direction. All right, so that this is a telltale sign, and they've done the correlation, and lo and behold, you can see from the plot, if there's a very small angle between the two pulsars, those tend to be correlated. So this one, if pulsar A is arriving a bit early, pulsar B right next to it should be arriving early, and that's what we see. On the other hand, you can see that if you go to 90 degrees, if pulsar A is arriving a little bit early, pulsar B now at 90 degrees is arriving a little late. And that telltale quadrupole pattern is the smoking gun for gravity waves. And I think the data look pretty compelling. Now, you may say, well, it's not so, this is good. This is really good. It is a 4 sigma result. It's a very, very difficult measurement. And the chance of this being a random coincidence is less than 1 in 1,000. So pretty compelling evidence. All right, what else have we done? So we often use the Green Bank telescope as part of an array. There's the thing called the GMVA, which is the global millimeter very long baseline array. And that includes telescopes all over the world. Green Bank is really good to use in that because of its large collecting area. It can the calibration is much better. The dynamic range is much better. It makes the whole interferometer better. It makes the image quality better. So this is an image of M87, which is a famous galaxy. If you remember the Event Horizon Telescope, the first black hole picture was of this. And the little inset there, you can see the kind of the ring from the black hole. That's the black hole. But what's really exciting about this is that little fan-shaped thing. That's showing the relativistic jet coming from that black hole, and it goes all the way down to the black hole. So we now can see where the jets begin. It's really, really close to the black hole. It's not far off in some large accretion disk. It's right down on top of the black hole. So that's for the first time we've been able to see that. That's pretty amazing. And finally, I'll show you two more things, both relating to radar. So if you remember NASA's DART mission, DART was supposed to slam into an asteroid and move it, deflect it from its orbit. And Green Bank confirmed that it was successful. So there's a little asteroid called Dimorphos that's in orbit around a bigger asteroid called Didymus. And it was the period of that orbit was 11 hours and 55 minutes. Afterwards, radar studies showed that the orbit had changed, and we were the receiving station of that. And you can see the little yellow circle is poor little, Dimorphos that was slammed into. And you can see we can trace its motion, determine its orbital period, and the new period was 11 hours and 23 minutes. So in fact, it did move. So this is really good. If ever an asteroid is bearing down on Earth, we may be able to deflect it. We have to make sure we deflect it out of the way rather than in the way. So we have to trust our calculations. And finally, this is a radar image where Green Bank was a transmitter. We built this little prototype transmitter, small transmitter, 700 watts, less than your microwave oven. And we transmitted from the Green Bank telescope and received that reflected signal from the moon with one of the VLBA antennas. And there's the image. And if I told you that this was a radio image, you wouldn't believe me. This is a radio image. How amazing is that? It is the highest resolution image of the moon ever taken from the ground. 1.25 meter resolution. And I'm just going to zoom in to show you some of that detail. That's just remarkable, right? You can feel the dust. You can see these. You can see my cursor. There are these little hexagonal things like there and there. That's new. No one has seen those before. So, you know, it's pretty amazing stuff. And we're hoping to build a new radar transmitter to pick up on some of this work. All right, so let's talk about, that's the science we do. Let's talk about the site. We have about 2,700 acres here. We have 48 buildings. There are 8 telescopes on site. 3 of them are being used now. We have houses, we have a dorm, we have a hotel, we have a cafeteria, some classrooms, and you're in one of the auditoriums. There are 2 quiet zones that surround Green Bank. One is the National Rated Quiet Zone, which is the large area you see in the map there. The star on the left is the Green Bank telescope. And the star on the right, anyone know what the star on the right is? Sugar Grove, yeah, the Sugar Grove listening facility. Now, if you notice, the quiet zone is not centered on Green Bank. So really, the quiet zone is more about them than us, but we are very happy to take advantage of it. Right. So what we do is coordinate all licenses for transmitters in the quiet zone. And we have the right of refusal of any company who wants to build a transmitter that would interfere with our work. There's another smaller quiet zone around the West Virginia radio astronomy zone. That's a 10-mile radius from the observatory, and that protects against any electrical equipment that could cause interference. So in principle, no one should have microwaves or Wi-Fi's or radars on their car. They do, some do, but it is a uniquely quiet environment here. I liken it to a national park. We're preserving quiet so that we and our colleagues at Sugar Grove can do their work. All right, some fun facts and figures. So there's one of the residents of Green Bank. I took that picture down by the airstrip just a couple months ago. It's our indigo bunting. We have about 100 people who work on site. We have a few more in the summer. We have some tour guides and cafeteria workers who join us in the summer. Our annual budget is about $14 million. About $9 million of that is from the National Science Foundation, and about $3.7 million of that is from contracts. Our 2 major contracts are the Nanograv and, oh, I'm sorry, I've moved, yes. Our 2 major contracts are the Nanograv Consortium and the Breakthrough Listen, the Search for Technosignatures. We have 3 active telescopes, the Green Bank Telescope, the 20-meter, which is mostly for educational use, but there is some commercial use, and the 40-foot telescope, which is education only. We have about 50,000 visitors per year come to our site. So what do we want to do to move Green Bank into the next decade? Well, one of the things we want to do, I've talked about, is we want to build this radar. We've demonstrated our low power system. We want to build a high power system, 500 kilowatts rather than 700 watts. We're working with our partners at the National Radio Astronomy Observatory in Charlottesville, the Central Development Lab, it's part of the NRIO, and our partners with Raytheon to develop a new kind of radar transmitter that is modular, array, solid state, mimic technology. So if that works, that'll be fantastic. There's no single point failures. It's not like a klystron that can just go kablooey. It is, you know, if you lose one element, meh, okay. And you can do some things, fun things with steering the beam around with the phases. We have a design review in November. We need to find more funding for it. We think we can. It'll be about a $40 to $60 million project, and will require some major surgery to the GBT. Our current subreflector is probably not a good idea for radar because it's a Gregorian focus, which means that if you illuminate the dish, you'll focus all that energy into a single point. Well, if you want 0.5 megawatt of radio power through a single point, good on you, but it'll ionize the air. You have the eye of Sauron. There'll be this big blue plasma ball. It won't work very well as a radar. So we have to get a Cassegrain focus, which means we have to get a new secondary that we can deploy in and out. So we'll have to design that. It's doable, but it will require some effort. The other thing we're working on is this beast called the ultra wideband receiver. And this is a receiver that goes from 700 megahertz to 4 gigahertz, which is quite a big bandwidth for a single receiver. We are working on some thermal issues, but the receiver does work. There's a pulse that we detected from a pulsar, and there's the waterfall plot on the bottom. That's a intensity versus time and frequency. So we can detect this thing over the whole range. We need to improve its sensitivity. We think there's some thermal issues that we understand, and there's a little bit of a design issue that we're cleaning up. But it is a beautiful piece of machinery. That feed horn is just gorgeous. If it doesn't work as a receiver, we can display it as sculpture. We're working on a new X-band receiver. This doubles the frequency coverage. So there it is. This is a pretty standard radio receiver. The old one went from 8 to 10, had an old refrigerator technology in it. This new one has better cryostat and more instantaneous bandwidth. The commissioning is complete. It's working. We've used it for radar. It's perfectly fine. If you notice right out here, right at the door, there's a new building on campus, and that's the data center. And the data center was specially designed to be shielded and provide a lot of power and a lot of cooling so that we can store our data. Right now, the data are not easily available to the community. We're going to fix that, but we need 100 petabytes or so of storage space. So this building is the thing that's going to house all those disks. And we're going to make all the data that was ever taken by Green Bank easily available to the community. The big thing that I need to do is refurbish the telescope. Now, the telescope is perfectly safe. We've been doing maintenance for a long time, but it's like an old car. It's 23 years old. And if you've ever had a 23-year-old car, there's only so much you can do with the old parts. You're going to have to replace some of the parts. And that's what's happening here with the Green Bank telescope. It was designed to last 20 years. It's now 23 years old. So, everything from here on is technically gravy. But it's such a great telescope, and we can fix it. We can refurbish it and make it good for the next 20, 30 years. So that's the plan. There are some issues. One surprise we had last January was a chunk of metal came out of one of the wheels. And you can see the hole there, right? It's like a fist-sized chunk of metal came out of the wheel. And that shut us down for a few months. The replacing wheel was actually kind of interesting. I didn't know they made jacks that held 16 million pounds, but they do. And it's like a change of the wheel on your tire. You have to jack it up, pull it off, replace it with a new one. Luckily we had a spare, and we're buying a bunch of new wheels. We never thought these wheels would break, and they were projected to last 140 years, but this one lasted 23. And what we learned was, back when they were building the telescope, there was a change of material from one drawing to the next that no one caught. And they didn't do the lifetime calculation. They changed the alloy of the steel, and the new steel doesn't live as long as the old steel would have. And so when we did the calculations, guess what? It should last about 22 years, and it did. So we had to buy a whole bunch of new wheels, and we are, and the NSF has funded us to do that. So we're buying a whole bunch of new wheels, buying a whole bunch of new bearings, whole bunch of new seals. It's like when your mechanic looks at your car, oh geez, you probably need a new alternator too, right? So that's what we're doing. Another area of concern is the foundation, and we're finding places in the foundation where the foundation is not solid anymore. It's kind of crumbly. Brian, our telescope engineer, was showing me this once, and he had his pocket knife out and said, "Here, look at this. You can dig right through there." So don't do that. Stop doing that. But it was like sand. So pieces of the foundation were crumbling. What we think we understand now is it's just due to the extreme weight of the telescope. So what happens is we have these grout pockets that support the wear plates. And that grout is slightly exothermic, and it expands ever so slightly when you put it in. And when it expands, it pushes the concrete around and out a little bit and makes cracks. Once you have the crack in the concrete, you get water in there, and then you have the freeze thaw cycle, and away you go. So that's what we think has happened. And there was a place in the foundation that was pretty bad. So that's a perennial problem with this telescope. We think we now know how to address it. We're going to do better. We're going to replace all the concrete, and we're going to use better grout for these grout pockets for the support. The track, as I mentioned, each piece of track each wheel carries about 1 million pounds. The track carries that in a small area. The track has been a perennial problem with the Green Bank telescope. There's only one rail system that carries more weight than the Green Bank telescope, and it was used exactly once. Can anyone guess what's that? It wasn't the shuttle, but it's a good guess. Chernobyl, the sarcophagus, was the only track system that carried a larger weight than we do routinely. And we move every day. So it's not really a surprise. It turns out that the steel is not behaving like the rail companies think that steel should behave. Under these extraordinarily large stresses, under these extraordinarily large loads, the steel is behaving slightly like plastic. It's like toothpaste. It actually pushes, it moves in the direction of travel. So it's not nice springy steel like in your textbooks. So anyway, we're coming up with some techniques to prevent the cracking that we see in the track. We do this thing now called ultrasonic peening. Like if you have your copper pot at home and you have hammer marks in it, that hardens the surface. We're doing the same thing on a small scale with ultrasonic techniques to harden the surface and to try to prevent some of these cracks. And then the big issue here is the coating. The paint is just worn out. It's 23 years old. It doesn't hold very well anymore. We have some spots that are corroded. When you go up the telescope, you'll notice there's some corroded spots. And this is a big job. Any guesses on what it would cost to paint the Green Bank telescope? Not the surface, but the backup structure, upper feed arm and the backup. 5 million, 20, 40. 40 million. I know. I was like, what? That's a lot of paint. That's a lot of paint. Then the issue is, yes, you're going to have to sandblast it or actually water blast it. You have to abrade it. You have to get the old paint off. You have to prime it, and you have to put 2 coats of paint on. So that's doable, and people who paint bridges can do that sort of thing. The difficulty with the Green Bank telescope is the access. There's just a lot. It's very difficult to get to a lot of the spots in the telescope. And so, it's the harnessing, the rigging to get people to the spot. That is the expensive bit. To paint just the upper feed arm, that's from the receiver cabin up, or the surface up, that's about 4.5 million alone. Just the feed arm. All right. So what do we want to do? So we're going to refurbish the infrastructure. The good news is the NSF has been chipping in. They gave us 4.5 million a couple of years ago for the track and the grout. They gave us 5 million this year for the wheels. We are confident that we are going to get this extra funding that we need. And remember, our baseline budget is $14 million a year. So an extra few million a year for the next 7-8 years is okay. It's not going to break the bank. NSF can afford it. We want to get our ultra wideband receiver commissioned. We want to get our data archive up and running, and we want to build a radar system. So those are the coming attractions for the Green Bank telescope. And in 5 years, when you come back and I give this talk, I'll show you how great that has happened. The challenges, of course, that I have is I need to find that money. I need to find the funding for the infrastructure. So far, NSF has been very good about it, and that's great. And so one hopes it'll just continue. We do have a funding model where we have to rely on contracts for some of our income. About 1/3 of our income is from contracts, and want to make sure that that continues, that we still can continue to attract our partners who can make up for the excess funding that we need. And one of the things that we face here, even in the rated quiet zone, is radio frequency interference. And the biggest threat is not from the ground, it's from the sky. It's all the satellite communications. They're totally unregulated. We have no say over what they can broadcast, how bright the signals can be, that we do have. There are international treaties that limit the frequencies that they can broadcast at. But some of those frequencies are good for us. So for instance, DirecTV sits right on top of a line of the hydroxyl molecule. That line is essentially gone to us. We're blind. You can't see it anymore. All right, so I'll stop there before I get into science. Are there any questions or comments or things you want to know about running the observatory? Yeah. 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 We're going to add about less than 100,000 pounds, but it's already 17 million. So it's not, it's a lot of weight, but it's not going to push us over the edge. That's right. Yeah. But it's a good question. I mean, we'll have to make sure we put it in a spot that doesn't hurt anything, right? But yes. And the plan is to put it at the base of the feed arm, not on top at the prime focus, but at the base of the feed arm and beam up toward the subreflector. Yeah. They were both about 13.8 gigahertz. So K band. Yeah. Yeah. So we tend to do just one project at a time because we have a single receiver that we use for each project. Now there's two modes that we use. One is the so-called open skies time. And open skies, any astronomer from around the world can propose. You could propose to our call for proposals and say, we want to use the Green Bank telescope. We're going to need 5 hours to achieve our scientific goal. Then they have to say what their goal is and how they're going to achieve it. And we have a committee that evaluates those proposals, rank orders them in terms of their scientific impact, and we do the best science we can. So independent of where you're from, what you do, if it's a good idea, it'll get on the telescope, right? We're oversubscribed by about a factor of 6 at some frequencies, a factor of 2 at other frequencies. The other mode we have is a contract mode where people actually buy telescope time, and then you do what you want. I mean, as long as if you have some idea, some crazy idea, well, as long as you're paying, that's cool. We'll take your money. It costs about roughly $2,000 an hour to run the observatory, so time is available. Yeah. We found that there's a bridge painting company called Liberty. I think they're out of Ohio that we like a lot. And they're bidding on the feed arm painting and the whole painting. We think the whole package is going to come in around $35 to $40 million. The feed arm alone will cost about $4 million above the cabin and another $4 million below the cabin. Yeah. Oh, yeah. So the chime telescope, the cylindrical one. Yeah. So that's those are colleagues with the Chime collaboration. It's a Canadian group, and they are interested in looking at fast radio bursts. So that's one element of an interferometer. There's another there are a few other telescopes like it in Penticton, British Columbia, and I think there's one other one at Hat Creek, California. And so they're using it as an array, and they have this funny beam shape because of the cylindrical design. So they focus to a line rather than to a point. And so they have this kind of rectangular patch of sky that they look at, and they wait for things to drift through. And they're waiting for things to go bang. They're looking for fast radio bursts. So they're just constantly monitoring the sky for new flashes of radio. It's looking at yeah. So it's looking it's looking at that chunk of sky all the time, and as things drift through, they see more of the sky. Yep. Yeah. Yes. Yeah. If you search it, it's I think Fortune 500 featured that as one of their best astronomy pictures last year.
Sorry, could you say that again?
My watch is complaining to me. Yes. I'm pretty sure you could find that on our website. Yeah. Yeah, it's a gorgeous image. Yeah.
What's the frequency?
The low frequency of the chime, it goes from about, I want to say 200 to 800 megahertz. It's a low frequency for our purposes. It's very low frequency. Yeah. Yeah. So we occasionally work with the VLBA, but we're not technically part of it. So sometimes when an experiment demands our sensitivity, we will join in. Yeah. Okay. Last one before we move on to science. Yeah. 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 It needs to be fixed. It's on the list to be fixed. Yeah. I live in the house right next to it, and it bothers me. Yeah. But we've had some other issues with asbestos in our houses that have taken priority. So, but it's on the list. It'll get done by the end of the summer. All right. So the second part of my talk, I'm going to breeze through a project that I've done called RAMPS. RAMPS is the radio ammonia midplane survey. It was done with this telescope. And of course, if you've ever had the wild leek called the ramp, they're delicious. They grow around here, and I name all of my surveys after food for obvious reasons. All right, so it's a bunch of my collaborators. This is a multinational effort. People in US, Japan, England, Mexico, Australia. Just a really fun team, people I worked with and enjoy working with. And a lot of the heavy lifting. The heavy lifting was done by my graduate student at Boston University named Taylor Hogg. So any triumph is his, any mistakes are mine. All right, so why do we care about high mass stars? High mass stars are rare, but they are important. If you look at a galaxy, you see the light from high mass stars. You don't see much light from the low mass stars. That's why galaxies look blue. They dominate the energy and the chemical input into the interstellar medium. When they explode, all that material comes for free during those supernova explosions. They disrupt the interstellar medium with H2 regions, these ionized regions, or supernova explosions. And they influence the formation of new stars because of all this energy they're pumping into the gas. This is a beautiful image of the high mass cluster there. It's the trapezium, and you can see kind of these fingers of God, and you can see the carve that has carved out a hole into the interstellar medium. So these guys pack a punch. The formation of high mass stars was much less well understood than the formation of low mass stars. That's because they're very rare. There are only about 10,000 O stars in the galaxy, compared with 100 billion total stars. Right, so they're very rare. Because they're rare, they tend to be distant, so you don't get very good detail. And they form inside of these dense molecular clouds, so optical astronomy doesn't work. The clouds are entirely opaque. So you have to observe at longer wavelengths like the infrared or the radio. We do have a broad understanding of how stars form, though, how high mass stars form. The basic unit of formation you can think of as the molecular clump. So this is a clump of dense gas. You see these all over the place. They contain about 1,000 solar masses worth of material, and they're about a parsec across. Inside of those clumps, you get these littler things, denser but smaller, and these things are called molecular cores. Their masses are a solar mass or more. They're about 10,000 astronomical units across, right? Size of solar systems, not the size of interstellar distances. And these are the things that are going to form the individual stars. Now, when I say individual stars, there's a caveat here. There's no such thing as an individual O star. They're always in binary systems. But when I talk about the formation of a star, I mean a star or a binary pair. All right, so now what happens when the star turns on? The early star isn't doing much it's not on the main sequence yet. It's deriving its energy from gravity, and it's called a protostar. It collapses and turns into a protostar. Once that protostar forms, it's infrared bright, heats up the volume, the dust around it, and launches these bipolar outflows. So you can see these beautiful jet-like structures emanating from these things. Then if it's hot enough, as it enters the main sequence, it will begin to ionize the gas around it. So an O or B star will ionize the surrounding material, form an H2 region, and that H2 region then expands. And eventually it will disrupt the clump. And if it's massive enough, if it's more than 8 solar masses, it'll blow up as a supernova. All right, so that's kind of the life sequence of a young star, and that's what we're trying to understand, how that all hangs together. So there are lots of ways that these stars can add energy to the medium around it. There's the outflows, there's the winds, and then there's the radiation. So even before the supernova phase, these stars are injecting a lot of energy into the surrounding material. Once a supernova blows up, clearly that's injecting a lot of energy. And how does that affect the formation of stars if a supernova hits that clump? Never been seen before until a few years ago, and I'll show you that data. So some open questions. What are the dynamical states of the youngest clumps? Are they supported by turbulence and outward pressure, or are they collapsing? Does the feedback from the young stars affect these clumps? Can you see the effects of that energy? Does forming stars make the gas? Does it make the gas hotter? Does it make it more turbulent? And finally, can feedback from a supernova influence the evolution of clumps? Can, just like the energy injection from a young star, can that supernova blast wave inject heat and turbulence into the dense gas? So I'm going to talk to you today about this RAMPS project. And for RAMPS, I used the Green Bank telescope to image the ammonia molecule. Now, ammonia is not only a great cleaning solvent, it is also a beautiful probe of the interstellar medium. There's a lot of interesting physics going on with ammonia. And one of the great things about ammonia is that there is a series of transitions called inversion lines, where the ammonia molecule, you can think of it as tunneling through, the nitrogen is tunneling through the plane. And so that gives rise to a transition at radio wavelengths, about 24 gigahertz. Now, because all these lines are coming at roughly the same frequency, but they are sensitive to different energies above ground, the different lines probe different temperatures of gas. The higher you are above ground, the hotter the gas needs to be for that molecule to be populated in those states. So ammonia is a great thermometer. So if you look at, so the red here is the 1,1 state, that's the lowest inversion state. It's only a few degrees above ground. And then the 2,2 is the green line there. That's a bit higher above ground. And then the bottom one is the 3,3, that's even higher above ground. By measuring the ratio between the 2,2 and the 1,1 lines, you can infer the temperature. If the 1,1 line is much brighter than the 2,2, the gas is cold. If the 2,2 is comparable in intensity to the 1,1 line, the gas is hot. So you have an instant thermometer, and it's easy to read. The other thing you notice are these guys. So the line is actually split into 5 different lines through the nuclear quadrupole interaction. And this is basically the internal, it's due to the fact that the nitrogen is football shaped rather than spherical, and its orientation interacts with the electrons in the molecule. Suffice it to say, though, that if you can use the relative intensity between the center line, which is called the main satellite, and the outer lines, which are called the satellite lines, but if the satellite lines are very bright with respect to the main line, there's a lot of material. The optical depth is very high. If they're very faint with respect to the main line, then there's not a lot of material. It's optically thin. So ammonia, just with one glance, you can measure how much stuff there is. You can measure its temperature. And of course, from the Doppler shift, you can tell how stirred up the gas is, the line width, and the velocity that it's traveling. So a lot of information is packed into this ammonia molecule. So we use the Green Bank telescope to make a large map of ammonia emission along the galactic plane. It took us about 500 hours of telescope time. It took us several years to collect all the data and to analyze it. And it's finally available to the public. And here is the map that we made. So this is the ammonia map of the galactic plane. Now, the plane is long and skinny, so I chopped it up into 4 bits and I just moved them under each other. But this is a long strip of the galaxy. And all of those dots that you see are real molecular clumps. None of this is noise. This is all signal. So there's a bit of an improvement over what had been done before. The bottom is the old state-of-the-art ammonia survey, and the top is the new ammonia survey that was done with the Green Bank telescope. And that shows you the power of the Green Bank telescope. Lots of collecting area and lots of pixels in this. I used the 7-pixel camera. So everything was just gorgeous and worked really well. We found 2,680 clumps, and all these clumps are the sites of current or future star formation. So now we have a big sample to try to understand what's going in them. And each clump is very well characterized. So let's take a look at that guy. We'll zoom in on that guy. So we can measure things like gas temperature. There's a map of the gas temperature. We can measure things like the optical depth or the column density. That's on the upper right. We can measure the amount of turbulence or how stirred up the gas is, the velocity of dispersion on the lower left. And we can measure the velocity of the material, how it's moving. All right, so we have this sort of data on all 2,680 clumps. All right. So now let's look and see if we can learn anything about star formation. So we can look in the infrared and see what phase of stellar evolution these clumps are in. And remember, as I said, it starts out very cold, begins to collapse, and then you form a protostar that heats up the material around it, and then you make an H2 region, you ionize the gas that kind of blows it up and lights up the material around it. So by looking at these infrared pictures, you can kind of tell at a glance what stage of formation these star-forming clumps are in. The upper left, nothing's going on. Stars haven't formed yet. It is quiescent. It's dark in the mid-infrared. And the upper right, you start to see these little red dots in the mid-infrared. And these red dots are the protostars. This is the star has formed, has begun to heat up the dust around it. Then it makes a ionized bubble or an ionized gas region, and that's what the H2 region phase is on the lower left. And you can extend that to an even more diffuse phase called the photodissociation region phase. So we've looked at all of our clumps and categorized them. We found those numbers. 829 of them we couldn't categorize, but we can categorize the rest of them very easily. We have about 300 quiescents, 383 protostars, 714 H2 regions. All right. So the first question we want to ask is, are these guys collapsing? There are some theories of star formation that say these things should be rough equilibrium, they shouldn't be collapsing. There's another group of theories called competitive accretion that says they're collapsing. And we can measure whether or not these things are collapsing by measuring its turbulent energy. Turbulence is a pressure that pushes out. It's like a thermal pressure, but it's unorganized gas motions. And that tends to push the gas out. The higher the turbulence, the more gravity you need to make it collapse. The place where the gravity and the turbulence fight to a standstill is called the viral mass. And then we can measure the mass of the clump directly from these techniques and come up with this ratio of the viral mass to the clump mass. Don't have to worry about that. The answer is, if this number alpha is less than 1, it's collapsing. It's unstable to collapse. If alpha is greater than 2, then it's expanding or unbound. All right? So we can measure this for each and every clump. So here we have the viral mass on the y-axis. We have the clump mass on the x-axis. And we've separated now into the blue area is the collapsing spot on the diagram. The bound is just bound or in equilibrium, and the unbound is the upper left portion of this diagram. So let's find out where our guys live. Well, here they are. So here are the data for our quiescent clumps. These are the young guys that haven't formed stars yet. And you can see, by and large, they're all in the collapsing portion of the diagram. Protostellar, same kind of deal. They all live in this kind of collapsing piece of the diagram. Now, once we start getting to the H2 region, you start to see the whole kind of plot move up and to the left. And that's because the H2 region is pushing back and making these things less bound. So there's an additional source of pressure in them. But, by and large, what we found is, and then this continues when you go on the photodissociation region. So you can see a nice sequence there. Very bound, not so well bound, maybe not very bound. So there's a nice progression there. About 80% of the massive quiescent and protostellar clumps are gravitationally collapsing. So that's a very nice thing. And they ought to be. They're going to form stars, so they better not be exploding. Right? So this is a very nice confirmation, but it's a nice way to quantify exactly what's going on, how fast they're collapsing, and that they are indeed all collapsing. So most young massive clumps are gravitationally unstable. Good. The second question that I wanted to ask, can we see the effects of star formation? Do stars add energy to the material around them? Do they make it hotter? Or do they make it more turbulent? Do they inject turbulent energy? So let's look at the panels to the left here. What I've done is I've broken out the samples into the quiescent, that's the youngest, the protostellar, that's kind of the teenage stars, and the H2 region, that's kind of the adult stars. And I plotted the distributions of their temperatures that we measure from ammonia. And it's not much, but you can see that there's a nice progression that the quiescent guys are about 12 Kelvin or so. They're cold, but as the stars form and as they evolve, they get significantly hotter. These H2 region ammonia temperatures are about 17 Kelvin or so, and it's significant, right? So the red here is the mean, and that's the error on the mean, and it's very significant increase in temperature. So we're watching these things heat up as they evolve. The same thing with turbulence, right? So this is the line width or the velocity dispersion, and you can see that as the stars evolve, these stars are injecting more and more turbulent energy into the clumps themselves. The lines get fatter and fatter. There's more disorganized motion, probably due to stellar winds. All right, so that's a nice thing. We're seeing the process of feedback happening, and we can begin to quantify it. So we see a significant increase in clump average temperature and velocity dispersion with the onset of feedback. Now, the next thing I want to talk to you about is a bit of a detective story. I didn't believe it. My student finally convinced me of it. And this is the first time I've ever seen a supernova slam into a dark cloud. All right. So here we have a dark cloud. This is the infrared picture of it. And there's this filamentary dark cloud. And we didn't think much of it because we see things like this all the time until we looked at the ammonia spectrum. The ammonia spectrum of this thing is really weird. A normal ammonia spectrum looks something like this. Thin lines that are a few kilometers a second wide. The line from this guy is this thing, and it stretches over 25 kilometers a second. It is enormously fat. It is the fattest line that I have ever seen, and I think it still is the fattest line on record for a star forming region. What is going on? Now, there's a bit of complication here. What I'm showing you is the ammonia 1,1 is in black, the 2,2 is in blue, the 3,3 is in red. There's something weird going on with the 3,3. There's that spike. We'll talk about that in a minute. And the 4,4 is in green. There's a lot of hot gas here. It's very stirred up. What is going on? Now, it's a bit complicated because there's actually two ammonia clouds along the line of sight. There's our source of interest. And the thing to the right is just an unrelated clump at a different velocity. So just forget about that. It has nothing to do with the source. All right, what's going on? Well, I didn't believe this, but then my student convinced me. Our cloud sits right there where that star is. And this is a radio continuum image of the radio sky at this at 20 centimeters in the continuum. And this beast is a supernova shell. It is a big old supernova that is expanding. You're seeing the synchrotron emission from the edge of the shell. And our guy sits kind of right on top of the cap of this thing. We also see here, there are some OH masers that are telltale signs of an interaction between a supernova and a gas cloud. And the yellow circle shows where we have extended very high energy gamma rays, TeV gamma rays, which is also associated with a supernova. So it took me a while, but I now believe what we're seeing is that this cloud is just was sitting there, minding its own business, when suddenly the supernova shell slammed into it. Okay, let's see if that makes a lot of sense. So one thing we did is to confirm this, we imaged this with a very large array, right? So we got a very nice detailed picture of it. And we imaged it in ammonia. And what we see here is the velocity of that ammonia gas. Now we have the resolution to zoom in on pieces of it. And the gas at this side of the cloud is all at about 80 kilometers a second. And the gas at this side of the cloud is about 60 kilometers a second. And again, that's astonishing. That velocity gradient is huge. You never see that. At most, you see a difference of a kilometer a second or two across one of these clouds. Here we're seeing 25. So the big fat lines are due to the fact that one side of the cloud is at one velocity, the middle is kind of at an intermediate velocity, and the left side of the cloud is at a different velocity. And you can imagine what happens if you're sitting there minding your own business, and then suddenly, boom, this blast wave goes past, you're going to get accelerated. So what we're seeing is the gas that's being accelerated. The gas that's at a different velocity is being accelerated. We also see an indication of a shock. So silicon monoxide is a molecule that indicates shock because it's formed from silicon. And the only way you can get a lot of silicon into space is to blast apart the dust grains that contain those silicate minerals. And whenever you see silicon monoxide, you know you have a shock. A shock wave has passed. So again, a smoking gun, evidence of a shock. The other thing we see, remember that funny spike on the ammonia 3,3 line? Well, that turns out to be a naturally occurring maser, just like a laser, but at microwaves. And an ammonia 3,3 maser is extraordinarily rare and is only found when you have a fast shock, when the shock is hitting something. And we see 4 ammonia 3,3 masers here. They're indicated by these colors here. And you can see the spike. All that signals from the maser, and there's a little bit of thermal below it. So the fact that we're seeing these ammonia 3,3 masers is another indication that we're seeing something unusual. Something's being slammed into here. And now here's what I think is really the smoking gun. Now remember I said the lower the transition, the colder the gas. So the ammonia 1,1 is tracing colder gas. The 2,2 is tracing warmer. 3,3 higher yet. 4,4, 5,5, and 6,6. Now, if you look at this, here's the ammonia 1,1, and this whole right side of the cloud is bright in ammonia 1,1. That's the cold gas. That's the gas that hasn't been hit yet. It's just minding its own business, but the stuff on the left has been hit, and it is getting really hot, right? So you can see as you climb the ladder here, when you get to this is tracing gas temperatures of hundreds of degrees, room temperature gas. And the ammonia 5,5 and 6,6 is only bright on the left side. So there's also this enormous temperature gradient in this cloud. The left side of the cloud is very warm. The right side of the cloud is very cold. So here's what we think has happened. This cloud was sitting there, and then the blast wave from the supernova hit it. It hit it on the left side. That's where you see the fat lines. That's where you see the big jump in velocity. It's changed its velocity. That's where you see the hot gas. And that's where you see these indications of shocks, all on the left side there. The right side, if we wait another 100 years, the right side is going to get hot and shocked as well. So, if it's longer than I will probably be doing astronomy, but maybe my graduate student will still be doing astronomy in 100 years, and we'll make these images and watch this thing progress. It actually is a very exciting prospect. We could probably see the passage of the shock by pinpointing where those masers are and watching them change year after year. So that's a project I want to do, to watch this shock propagate through there. but it's kind of cool. Now it's a little bit of stamp collecting, but it's really neat. And what we've seen is the turbulence in this cloud is so huge that any star that's trying to form doesn't have a chance. The pressures are too big. So the supernova has effectively shut off any chance the star has of forming a star. So from this evidence, we conclude that supernovas end star formation in these clouds. So to conclude, we found that from our RAMP survey, most clumps are collapsing under their own weight. We see the feedback because we see evidence for increasing temperature and increasing turbulence. And we see this beautiful passage of a supernova shock in a dense cloud. And we see the gas being accelerated, heated, and having turbulence added to it. Thank you for your attention. Appreciate it. Questions on the science piece? Yeah. So the ammonia data were taken at 23.7 to 24.1 gigahertz. The VLA images of that synchrotron radiation, that was taken at 20 centimeters.